Hi, for this video we're going to be talking about random forests. The big idea of a random forest is that we're going to take a whole bunch of decision trees that we're using random variables, random observations to build, and as a collection we're going to have a forest of decision trees and we're going to put them all together to make our predictions. And this is a very effective way to make predictions using data. This is my #1 go-to for this type of problem when I have like spreadsheet data. All right, so random forest is a machine learning algorithm that can handle regression problems. So like when I have a numeric target variable, classification for categorical data, and survival analysis. Now, it can be used for predictive analytics and inferential analytics, but the inferential aspect is kind of limited. There is some good stuff in there, but really usually we're going to be using regression if we want to make an inference. So random forest is a type of ensemble model. Basically that means I'm taking a whole bunch of models together, I'm putting them together, and then I use the collection of all the models together to make one prediction. And then that on the ensemble of models is how I come up with my conclusion. All right, so what we're going to do when we build these, we're going to take a subsample of our observations, we're going to take a subsample of our predictors, and when these are going to be randomly selected, and then we're going to make a decision tree. And we're going to repeatedly do this for each tree. We take a subsample of our observations, we take a subsample of our predictors, and then we make a decision tree. And we do this over and over and over. And typically, we're going to have 50 to 500 decision trees. 50 trees is what the default state is for SAS Enterprise Miner. The default for Random Forest and Ranger, I believe, is 500 decision trees. Now, the more decision trees you have, usually you'll get a better prediction. But the downside is that you increase computation time, so you have to find that balance. This is a pretty fast algorithm as long as you implement things well. So 500 usually is not doesn't take too long to work with. But if you're finding that it's taking too long, go ahead and reduce the number of trees down to like maybe 250 or 200, maybe down to 50, depending on how much speed you need. All right, so what we're going to do when we make a prediction, if I have a numeric target variable, all of my decision trees are going to make a prediction, and it's going to be a numeric prediction. Then we're going to go ahead and average all of them together. If we have a categorical target variable, what it's going to do, all the different trees are going to basically vote on what they believe the prediction should be, and the prediction that has the most votes is the one that we have for the conclusion. Now, something that's nice for this is that we can get an estimated probability of each category by just saying the number of votes corresponds to the number of probabilities divided by the number of trees. This works really well for the problem that we're going to be doing in the example below. Now, there's a lot of good advantages with decision tree, with random forest. So first of all, they're very good at detecting which variables are important. So if I want to go and do variable selection for another problem, one option that I have is I can build a random forest. I can look at which variables are important, and then the other model I want to use, let's say I want to use regression because I have to use a regression model for work. It just has to be that way for the project. Maybe my supervisor only trusts regression, something like that. Well, I can use random forest to see which variables are good for the project and use those only in my regression model. This is something I've done at work several times. One thing that's very nice, random forest automatically handles interaction terms for you. So it doesn't tell you what the interactions are, but it takes care of it under the hood. You don't know what's going on, but it's resolved for you. We need very little data preparation for these types of models. Skewed data will not reduce model performance, which is very nice. Now for the variable selection, what we can do, the predictors that are used more often are the ones that are more important. And Overall, this is very good predictions for the amount of work needed. Now, some disadvantages. And this should say random forest. I'll go ahead and fix that. They are difficult to interpret. There are interpretations and inferences that we can get using special functions, but really when you look at the model, it's not clear what it's trying to tell you. There's no indication of how the predictors relate to each other, so we don't know which variables have an interaction effect when there's interaction going on. There may be none, there may be a whole bunch. We have no idea from what's spit out for us. And we don't see anything like correlation. We don't usually have something like a hypothesis test to tell us which variables relate to the target variable very well. So now something that's kind of interesting about random forests is that if you look at the implementation and the actual code, they actually build individual trees that are too deep. So like individually, each tree is not a good predictor. Remember from decision trees from the previous video, we went through and we tried to make the best tree possible, not too shallow, not too deep. Here, almost all of them are too deep. But what happens is that when we average them out together, it ends up being a pretty good model. This is something that's a nice feature, and this also adds some variability so we can get better ideas of things like standard error and things like that. In R, there are two major packages for random forests. There's Random Forest, big surprise, and the Ranger package. Random Forest is very good if you want to have supported functions, if you want to do the inference aspect. This is a good default package to use. The Ranger package is a lot faster, and it's the one I usually use, but not always. Sometimes what I'll do is, if I want to figure out what's going on, like I need to use Random Forest, but it's taking too long, I'll use Ranger, find what parameters work the best, apply it to Random Forest, and then move on that way. That's a personal tactic that I use at work. Now, in my experience, the two packages are about equally solid at making predictions. So Random Forest is just much better supported for inferences and visualizations and other aspects, but Ranger is a lot faster. So let's go ahead and let's do an example. Let's take a look at surviving on the Titanic. So here's what we want to do. We want to take the Titanic data set and we want to look at the aspects of the passengers that we know about, and we want to build a model that would predict if someone will live or die. So if we decide to go, hey, let's go back in time and take a cruise on the Titanic, I'd like to know if I would survive. Now, the first part of this is the same from the previous video. I have to load the data. Then I look at the data just to see what's going on. This part doesn't print well, but on your screen, if you run the head of the data set, it'll look a lot better. Now we do our data prep. I change the order of the columns just so that I have the target variable on the far left, and I have my categorical variables, my ordinal variables, and then my numeric. I like to do that. I find that's an easier way to stay organized and helps me understand what I'm doing as I work through the data prep process. So now that I've also reduced down the data set to fewer variables that I know that I'm going to use. And the default format is 0 and 1. So what I'm changing it to is if it's a 1, it's a survived. If it's a no, it died. So when I get my averages and my mean and my probabilities, it's a probability of survived is what I'm looking at. And here's a table of what's going on. And here is, so let's go ahead and look at the cabin data. It's a categorical. I can see that it's not very informative as is. There's too many levels to it. Like the most frequent one is only 6, and then I have over 1,000 blanks. So let's go ahead and change it so that basically we're saying, do we have cabin data or not? That's all there is, just to make it a little bit simpler. And now we have a table for that. Now let's look at the embarked aspect. So here what we're doing, we're just, again, simplify it, where we have missing value. We have two missing values. So we don't know where they came from in the data set. So what we're going to do, we're going to bin it with C just because that's convenient. And here we have passenger class. First class is the best one. So I'm going to go ahead and convert that to ordinal, with first class being like what's considered the greatest class. And you see that it's the order switches. It went from 1, 2, 3 to 3, 2, 1 because now 1 is considered the greatest. Now, another field that we have in the data is the number of siblings and spouses in that's on the ship, and that's integer data. Now let's go ahead and take a look at the histogram. Oh, it's skew right. Now, since I'm doing a tree-based model, skew doesn't matter to me. I don't care. If I was doing regression, I would want to transform this with maybe a log transform or box Cox. Now here, let's number of parents or children on the ship. Once again, integer data. Let's take a look at the histogram. Skew right, but it's not going to impact the data. Now I'll start taking a look at age and other numeric variables. All right, well, I'm just going to leave it as is because I don't care what the shape is for this problem because we're using a tree model. And now we've got the fair. All right. So now that we've got things cleaned up, let's take a look at our data. Take a look at the summary of it. Oh, we've got some missing values. So let's go ahead and fill in missing values with just the median of the data set. It's a very coarse way to do imputation, but that's not the focus of this video. All right, so now what we're going to do, we're going to go ahead and we're going to manually build a random forest using the rpart package. So I'm going to make 4 different trees. It's a very small forest. I just want you guys to see how this looks. Now, something about this. When I go through, I do my random selections on my observations and the random selections on my variables. I'm not going to overfit like I would with a standard random forest algorithm. I'm going to do this in a manner that is a default rpart implementation, just so it's a little bit simpler, easier to work with. And we're only making 4 trees because I want us to be able to see what's going on. Realize that if I was doing an actual real random forest model, I would be building at least 50 of these trees. So what I'm going to do, I'm going to create a list of the different trees. And here is the number of rows of the Titanic. Here are my predictors. And we're creating 4 trees. And I'm using a random number generator, so I'm setting the seed so I can reproduce the results later down the line. And this is my vector of rows, 1 to the number of rows, vector of columns that I have in my data set. And repeatedly, for 1 through 4, I'm going to create a decision tree, and then I'm going to store it in this list. And the first tree gets in the first position, the second tree in the second position, and so on. That's what the double brackets J represents. J is 1, 2, 3, or 4. All right, now let's take a look. Let's go ahead and plot it. I'm using the lapply function to plot everything. And like, oh, hey, what's going on here? Okay, so here our first tree, it said that the only variable that's useful is the sex of the person, and which is consistent with what we saw last time, that sex was the most important. Now if I look here, I see that sex is important, and sex is important. All right, so now every single time, basically these trees say, if you're male, you die. Male, die. Male, die. Male, die. This sucks. I do not want to be on the Titanic. Now, let's say you're female. Well, these trees break it down a little bit more precisely. So if you're female and you have very few siblings or spouses with you, you're more likely to survive. If you're female and you have a lot of spouses and siblings with you, it's saying that you're probably going to die. But that's just one of the trees. If I look closer to all of these, we can see a little bit more. See if we can zoom in a little bit. Doesn't print out that well on this implementation of Word, but we can see passenger class is the variable that's next important after gender on this one, and then after that it's fare, which will go along. So passenger class and fare is what decides if you live or die as a female in this decision tree. So when we make a prediction, we're going to have 4 different predictions, and we're going to put them all together to see what does the overall collection, the random forest says, what is the probability of living or dying. All right, now let's take a look at the box. So we're going to print the box plot to see how, the probability of surviving from our model given the outcome of survived or died. All right, so we can see that nearly 100% of those who died have a very low probability of surviving. We have some outliers here, and we can see that almost everybody who survived had a probability of around, let's say, 0.7 or better. Oh, all right. Now there's a few passengers down here in this tail, and there's at least one outlier here, maybe more. There could be overlap on this, but it's not too bad of a model. And this is the modeled likelihood of survival. All right, now let's go ahead and let's implement the Ranger package. This is a package I like to use for work a lot. This is well developed, it's well supported for building random forests, and it's fast. I can get through the project quick, easy peasy, lemon squeezy with this package. So what I'm going to do, I'm going to build the Ranger Titanic object, which is going to be from the Ranger package using the Ranger function. Here's my formula. Survive depends on all variables in the data set. Remember, I filtered out some variables earlier, and probability is true. All right, so what this does, this line right here tells the Ranger package that I want the probability of survived. I don't just want the conclusion. If this is set to false, or I don't have the probability set to true, like I just don't address it at all in the code, what it's going to do, it's going to say survived or died, and that's all it's going to give me. It's not going to give me any more information. So I don't think that's as interesting. I want to actually see the probability. It's a little bit more precise. So I'm going to go ahead and set that to true. So now let's take a look, and let's see what we get. All right, so here's the call for the code. It has 500 trees. The sample size was over 1,300. We have 8 independent variables. For each tree, it only tried 2 variables. That's interesting. It's only 1/4 of our data. Oh, that's not as much as I thought. Generally, this value for the number of variables to try is going to be about the square root of the number of independent variables. All right, so 8 is a little bit less than 9, right? So the square root of 8 is between 2 and 3, so it took between 2 and 3 rounded down to 2. And I did not specify the variable importance mode. That is if I want to do some inference with this. For this video, that's not important. And for splitting, it uses the Gini criteria. And now here's something interesting. Here's the error rate. It gives me an estimated error rate of about 11%. And that's pretty good for the amount of work I put into this and the amount of observations I have. So, that's pretty slick. That's pretty neat. Let's take a look at the box plot of the probability of surviving given that they survived or died. Okay, so what we have here all of the passengers that survived are in this box plot. All the passengers that died are in this box plot. And when I look here, I can see that over 75% of those who survived had a modeled probability of surviving better than 0.6. I can see that everybody who died, about nearly all of the passengers that died, had a modeled probability of dying of less than 0.4. Now there are a good number of outliers in here floating around, but overall this is pretty good, and my accuracy ended up being about 11%. And so for the amount of effort I put into this model, that's pretty good. I could do better. I've done better in the past with this data set, but that's good enough for now. All right, so that's all I've got for you. I hope you're staying safe. I hope you're staying well. Please let me know if you need anything. Take care and bye.